Scientists just saved Moore's Law with 3D silicon chips. Source: University of Illinois Grainger College of Engineering research published in Nature. For more than half a century, the extraordinary growth of computing power has been driven by a simple idea: make transistors smaller and pack more of them onto a silicon chip. This trend, famously known as Moore's Law, transformed room-sized computers into smartphones, more powerful than the supercomputers of previous generations. But today, the semiconductor industry is approaching one of its greatest challenges. Transistors are now so small that engineers are beginning to run into the fundamental limits imposed by physics itself. As components approach atomic scales, quantum effects, heat dissipation, and manufacturing complexity make further miniaturization increasingly difficult. Many experts have wondered whether Moore's Law is finally reaching its end. Now, researchers at the University of Illinois Grainger College of Engineering may have discovered a way to extend the computing revolution by changing not how chips are built smaller, but how they are built taller. Instead of continuing to squeeze more transistors onto a single flat surface, the researchers have developed a breakthrough manufacturing process that allows silicon circuits to be stacked vertically in multiple layers, creating true three-dimensional chips. The concept is similar to the difference between expanding a city outward with endless suburbs versus building upward with skyscrapers. Both approaches can accommodate more people, but vertical construction uses space far more efficiently. In computing, stacking circuits vertically could dramatically increase transistor density, reduce communication distances inside chips, improve performance, and lower energy consumption, all while avoiding some of the physical barriers that have slowed traditional scaling. To understand why this is so important, it helps to consider how modern chips are currently built. Nearly all processors, memory chips, and AI accelerators are fundamentally two-dimensional structures. Billions of transistors are arranged across a flat silicon surface, connected by intricate networks of microscopic metal wiring. As engineers add more components, signals often need to travel longer distances across the chip, increasing latency and consuming more power. This problem becomes especially severe in artificial intelligence systems, where enormous amounts of data must move continuously between processing units and memory. Researchers have long recognized that stacking electronic circuits vertically could solve many of these problems. By placing layers of transistors directly above one another, chips could contain far more functionality within the same footprint. Data would travel shorter distances, communication bandwidth between layers would increase dramatically, and overall efficiency could improve substantially. The challenge has never been the concept itself, it has been the manufacturing. Today's commercial 3D chip technologies already use forms of stacking. Technologies such as high-bandwidth memory and advanced processor cache systems are created by manufacturing separate silicon wafers and then bonding them together. While effective, this approach has limitations. The vertical connections between layers remain relatively large, and alignment precision is restricted. What engineers have truly wanted for years is something called monolithic 3D integration, where each new circuit layer is fabricated directly on top of an existing one. This would allow much denser vertical connections and dramatically greater performance. The obstacle has always been heat. Manufacturing high-performance silicon transistors typically requires temperatures approaching 1000 degrees Celsius. But once a lower layer of circuitry has already been completed, exposing it to such temperatures would destroy the delicate metal interconnects and components underneath. Industry standards generally limit additional processing temperatures to around 400 degrees Celsius after the first layer is finished. For years, this thermal barrier prevented researchers from creating true monolithic 3D silicon chips. Many previous attempts tried alternative materials such as polycrystalline silicon, metal oxides, carbon nanotubes, and two-dimensional semiconductors. While some showed promise, they often suffered from lower performance, reduced reliability, or compatibility issues with conventional silicon electronics. None fully matched the quality and consistency of the single crystalline silicon that powers modern computing. The Illinois team approached the problem differently. Instead of growing new silicon layers at high temperatures, they created ultra-thin silicon nanomembranes from a separate donor wafer and transferred them onto completed circuit layers using a low-temperature process. These membranes are astonishingly thin, only about 10 nanometers thick or less. For comparison, a typical silicon wafer is between 500 and 700 micrometers thick, making these membranes tens of thousands of times thinner. Because the membranes are so thin, they become mechanically flexible and can conform closely to underlying surfaces. This flexibility helps eliminate defects that commonly occur when attempting to bond rigid wafers together. Most importantly, the transfer process requires temperatures of only about 200 degrees Celsius, comfortably below the thermal limits that previously blocked monolithic integration. The researchers also redesigned the transistors themselves. Conventional transistor fabrication often relies on doping processes that require temperatures above 600 degrees Celsius. To avoid this problem, the team used a design known as a junctionless transistor. Instead of creating complex doped regions after fabrication, the silicon is uniformly doped beforehand. The ultra-thin silicon layers still allow precise electrical control while maintaining strong performance and avoiding high-temperature processing steps. Using this approach, the team successfully built 3 stacked layers of silicon electronics, each containing 625 transistors. The results were remarkable. Manufacturing yields reached between 98 and 100%, indicating exceptional reliability. Performance matched that of conventional silicon transistors fabricated using much hotter processes and significantly outperformed previous monolithic devices built from alternative materials. The researchers then connected the layers using vertical metal interconnects and demonstrated fully functional 3-dimensional logic circuits and memory structures. This is particularly significant because memory systems, such as static random access memory, or SRAM, are found in virtually every modern CPU and GPU. By distributing memory components across multiple vertical layers, future chips could pack far more functionality into the same physical area, while simultaneously improving speed and reducing energy consumption. The implications for artificial intelligence may be especially important. Modern AI processors increasingly face bottlenecks, not because computation itself is too slow, but because moving data between memory and processing units consumes enormous amounts of time and energy. Monolithic 3D chips could dramatically shorten these communication pathways, enabling faster AI training, more efficient inference, and significantly higher computational density. Perhaps the most exciting aspect of the breakthrough is scalability. The researchers emphasized that their process is not limited to 3 layers. Additional layers could potentially be added while maintaining high performance, low variability, and strong manufacturing yields. In principle, future chips could contain many vertically integrated layers of logic and memory, dramatically extending the performance growth that Moore's Law has delivered for decades. The technology has already attracted attention from major semiconductor industry partners, including IBM, Intel, and the TIA. Taiwan semiconductor manufacturing company Baidu. Researchers are now preparing to transfer the process into industrial semiconductor foundries, an important step toward commercial deployment. While significant engineering work remains before the technology appears in consumer devices, the proof of concept is highly compelling. For years, many experts have predicted the end of Moore's Law as transistor miniaturization approaches fundamental physical limits. This breakthrough suggests that the future of computing may not depend on making transistors smaller, but on building silicon electronics upward into 3-dimensional structures that unlock entirely new levels of density and performance. In many ways, the semiconductor industry may be entering a new architectural era. The age of flat chips could gradually give way to the age of silicon skyscrapers, where computing power grows not by shrinking endlessly toward the atomic scale, but by stacking layer upon layer of intelligence into the same piece of the same piece. silicon.no. If successful, this approach could keep the computing revolution moving forward for many years to come.